So numerical methods in engineering and sciences, most of them try to reduce engineering problem, a physical problem, into a set of matrix equations. The reason that they try to do that is because for matrices, for inversion of matrices, finding eigenvalue of matrices, there are very robust numerical techniques available. These techniques are very well developed, and we know a lot about these techniques. We know what are their pitfalls, we know when they fail, we know what their errors are, and so on and so forth. So there are very trusted algorithms, robust algorithms that are available for applying linear algebraic techniques to uh, invert matrices, find their eigenvalues, and perform a host of other operations on matrices. So it's for to solve problems on the computer, it's a very good idea to somehow reduce it to a set of matrix equations. Now, there are many methods of doing it. Finite element, on which we will be spending the rest of the course, is one method of doing it. There are other methods. Some methods are just common sense methods. They work for very simple problems, and there are more structured methods as well. So let me give you in the first class a set of examples in which we take problems, engineering problems, and convert them into a set of matrix equations that we need to solve in order to get the answers. It's not that the problems that I'm going to take up, it's not that they are they cannot be solved by other methods, but we will solve them by, we will convert them into matrix techniques. We will not really solve them, we will convert them into matrix equations, and um, and see what are the ways available for us to do it. So the first problem that I'm going to take up is a problem of springs and masses. So I have three masses, M1, M2, M3. This is a static problem, and what I need to know is I can apply displacements U1, U2, U3 on the three masses, or forces R1, R2, R3 on the three masses, or I can apply a combination of them. I can apply U1 on the first mass, R2 on the second mass, R3 on the third mass, something of that sort. So in order to find out the deformation of this combined structure in response to a combination of U1, R1, U2, R2, and U3, R3, I need a relationship between U1, R1, U1, U2, U3, and R1, R2, R3. In other words, I want to know that if I vary one of them, how would the other vary? All springs are Hookean, so they are like linear springs, K delta kind of, F equal to K delta kind of springs. And we will derive the matrix equations for this system, for the static response of the system. The loads are applied slowly. None of the loads or displacements are fluctuating loads or displacements. They are static loads. So this is a completely static problem. So every part of this problem satisfies equilibrium. So forces are balanced on any part of the whole system that we draw a free body diagram of. Okay, so apart from the fact that everything is in equilibrium, so we have to satisfy equilibrium conditions for each and every component, however small. Apart from this, we also have constitutive equations. We also need constitutive equations, which is in the form of the fact that the springs are Hookean. So each spring has a linear force displacement relationship. So armed with these two facts, we can now go ahead and draw the free body diagrams of each spring and each mass. So we will take this to be the positive x direction, and then the free body diagram of the first spring, let's say, whose constant is k1, is, we'll apply a force on it, and we'll call this force F1, 1. So it's applied by the mass 1 on spring 1. So this is how we are going to write it. And the displacement of this point is obviously the displacement of mass 1, which is U1. Similarly, for K2, we can draw the free body diagram. So K2 will have a force F2 applied by mass 2 on spring number 2, its stiffness is 2, and another force which is applied by mass 1 on spring number 2, and displacements here will be u2, that's the displacement of mass 2, and here it will be u1. We are taking everything in the positive x direction, which means that now uh, this is in the positive x direction. So if we draw the free body diagram of M1, we have a force F11 acting on it. We also have a force F22 acting on it. Similarly, we can do it for 3, and here we will have F2, 3, and here we will have F23, here we'll have F23 as well, and here we will have F13, whereas this point is u2 displacement and this is u1. Similarly, we can do for K4 and K5, and this mass, for example, will also be subjected to F24, and of course there's this externally applied force R1, so that the when you draw the free body diagram of this mass, you will have F11 plus F24 plus F23 plus F22 equal to R1. This will be the equilibrium equation for this mass, whereas these are for the free body diagrams for the individual springs. I have not drawn it for K4 and K5. This is done in the next slide. So you have all the free body diagrams of all the springs, and then we can write the equilibrium equations for each spring. So for example, for K2, we must have F12 plus F22 equal to 0, which means F12 is equal to minus F22. But we know that F22 is equal to K2 times U2 minus U1. So F12 should be minus K2 times U2 minus U1. So with this, so here we are using the equilibrium equation, here we are using the constitutive equation of the spring. We can do this for all the springs. This is what I have done, and write down the equilibrium equations and constitutive equations together in these forms. So this is for spring 2, for spring 3, and so on and so forth. We have for spring 1, we have just only one displacement because this point is fixed. So we have K1E1 equal to F11. This is the only equilibrium plus constitutive equation for the spring, right? So here we are taking the root of a force balance, and as a result, now that we have expressed the forces in terms of the stiffnesses, we can now go back and write the free body diagram, write the force balance equations for the masses. So this is for mass 1. Similarly, we can write it for mass 2 and mass 3, and then replace these forces by the constitutive equations that we have used. So if we do that, this is for mass 1, this is for mass 2, this is for mass 3, and now we will replace these by the constitutive equations that we had found from the free body diagrams of the springs. So these equations we'll replace them with, and then we have a relationship which has displacements only on the left hand side. On the right hand side, there are only external forces. So these external forces, we can write them as a vector. We will call this vector as F. These displacements, which we call generalized displacement sometimes, so these will be written as W, and this whole thing this whole thing is kind of the stiffness of the whole system. Now the stiffness does not connect a single displacement, a scalar displacement with a scalar force, but it connects a bunch of displacements at different points in the structure to a bunch of externally applied forces at the same points on the structure. And this connecting quantity is now a matrix, which we will call the stiffness matrix K. So this is the stiffness matrix. And if you plug in the constitutive equations, um, constitutive forms of these forces from this slide into these sets of equations, this is the stiffness matrix that you will get. So we will write it as Ku equal to F in analogy with the familiar expression for a single spring K delta equal to F. So now K is a stiffness is a matrix, U is a set of generalized displacements, and F is a set of uh, generalized externally applied loads. Now, uh, obviously, if you have applied a set of forces on this spring mass system, R1, R2, R3 are known, and then you just invert this, you just do K inverse F to get the displacements. If you know all the displacements, if you know the displacements, all three displacements on the three masses, you multiply this matrix and get the forces. It is also possible that you know U1, R2, and R3. That's what you have applied. In that case, also with a little bit of effort, you can get U2, U3, and R1 from these equations. So these equations sort of give you your answers to any combination of generalized displacements and any combination of generalized external loads. Now we have derived this equation. We have derived this equation, and this is going to be a very important kind of equation for us. We have derived this from force balance. There is another way of deriving it, which is from energy principles. And the idea is this, and the idea you are actually familiar with. You have done the Castigliano's theorem, and Castigliano's theorem is a special case of what I'm going to describe. So the more general setting of the Castigliano theorem is the principle of minimum potential energy, which states that the potential energy of a structure at equilibrium is at its minimum. So the potential energy of a structure is a minimum at equilibrium. The potential energy of a system, which we are going to call pi, so this is the potential energy of the system, is defined as the strain energy stored in the system minus the potential of the loads, potential of the external loads. So this combination, U minus W, has to be a minimum if the system is in equilibrium. So this gives us alternate, and in our case, a very important route to finding the equilibrium equations. Here we do not go by force balance. We do not go by force balance, but we take a completely different route, which I am going to explain through this small problem. We will come back to this and do this in much more detail. Now let us look at the potential of the loads, work done by the loads. So we had defined this U, which is the generalized displacement vector U1, U2, U3. We have also defined this F, which is the generalized external force vector R1, R2, R3. And the work done by these force displacement combination is obviously U1 R1 plus U2 R2 plus U3 R3. All of them are in the same direction. So when you take the dot product, they just multiply. And this whole combination can be written as U transpose F, because U transpose is U1, U2, U3 as a row vector, and then R1, R2, R3, which is the F. So if you multiply, you get U1, R1, U2, R2, U3, R3. So W can be written as U transpose F. Okay. Now, we can do one more thing to calculate u. To calculate u. To calculate u, what we do is we can go back here. We can go back to this, and we have these k and u relationships. Okay, so the energy stored, the strain energy stored in this spring is half k1 u1 square. The energy stored in this spring is half k2 times its deflection, its stretch, which is u1 minus u2 square. Similarly, this is k3, half k3 u2 minus u1 square. This is half k5 u3 minus u2 square, and this is half k4 u3 minus u1 square. So your u, the total strain energy stored, is sum of these quantities, and so on. And then we had defined this stiffness matrix, not defined, we had obtained this stiffness matrix. If you take this stiffness matrix, you can easily show that this u can be written as half. I don't know what went wrong. Yeah, it can be easily written as, this u can be written as half u transpose k u, which is a matrix equation, but in the end this is going to give you a scalar. Why? Because u transpose is 1 cross 3, k, if you remember, is 3 cross 3, u is 3 cross 1, so finally you get 1 cross 1, or a scalar, and that scalar will exactly be equal to this long sum that we have. So I leave it to you to prove. You should be easily be able to prove that u is half u transpose ku. Again, you see the analogy with half k delta square. So delta square, you can write it as delta k delta. So that's what we have done. U is the generalized delta, k is the generalized stiffness, and u again is the generalized delta. So this is exactly analogous to half delta k delta. Okay, which is what you are familiar from the equation of a single spring. This is not for a single spring, but for an assemblage of springs. Okay, now so we have this. We have you are going to verify that u is indeed equal to half u transpose ku. So then pi is half u transpose ku minus u transpose f. So this is what pi is. This is what pi is. And now we have to minimize this, which means that if we take u1, u2, u3 to be the independent variables, we must ensure that del pi del ui, I going from 1 to 3, is equal to 0. That gives us three equations, and these three equations have to be satisfied because the principle of minimum potential energy demands that pi must be a minimum um, at equilibrium. So at equilibrium, these three equations must be satisfied. You might ask at this stage that how do I know that this gives me a minimum? It can give me a maximum as well. But for linear elastic problems, we are going to prove this in great detail later. For linear elastic problems, the maximum is known to be at infinity, and there's known to be one single minimum for most problems, one single minimum, and that means that the solution to these three equations will always give me a minimum that is guaranteed for certain sets of problems in certain sets of commonly encountered problems in mechanics. These three equations are going to give me um, the minimum. So in order to minimize this, this is what I'll have to do. It will turn out that these three equations, del pi del u1, del pi del u2, del pi del u3 equal to 0, are nothing but the equilibrium equations that we have obtained before. Again, I want you to check this formally, that if you now write this whole thing down as a function of u1, u2, u3, and write this whole thing down as a function of u1, u2, u3, and then take these derivatives del pi del u1, del pi del u2, etc., and set them to 0, then you get back the same set of equilibrium equations in which in the matrix form are ku equal to f, as we had got by simple force balance that we did here. Okay, so force balance will give you the equilibrium equations. Energy minimization will also give you the same equilibrium equations. They are completely equivalent principles, completely equivalent procedures. They'll lead you to the same set of equations. That's point number one. You can use either to derive this equilibrium equation. You need two things to derive this equilibrium equation. One, you need a force balance equation, principle of force balance, and you need a constitutive equation for all the constituents in your system. Once you have these, you can use either force balance or the energy principle in order to derive the uh, equations, the final matrix equations, which we call the equations of motion. Uh, in finite elements, we generally take the energy root, and not generally, we always take the energy root, and there are very strong reasons in favor of that. We will uh, discuss those later as we go along. I just wanted to give you a flavor of how these equations can be formulated. Another basic problem in engineering in solid mechanics, but this will lead to a little bit of a different kind of matrix equations. Let's see. So the problem is that I have two beams, two rigid bars actually, of length L, which are completely vertical, exactly vertical, subjected to a perfectly vertical force. The stiffnesses are all here. It's connected by two springs, K and K, to the walls, and then there's a rotational spring of stiffness Kr at this joint. Now, the question that I'm asking here is that if I displace this slightly, or maybe I can ask it in a different way, what is the value of P at which a slightly perturbed um, sideways perturbed structure would still be in equilibrium? Okay, so in other words, what are the values of P at which this structure is going to buckle? Okay, it is going to deviate from its vertical solution. Obviously, when you apply P, it's this point can go vertically downwards, but what is the value of P where a sideways shifted solution would also be a solution to this problem? That's the question that I'm asking here. At what values of P is this structure going to undergo buckling? To do that, we assume that the displacements are small, the perturbations are small. So you have two generalized displacements. One is the displacement of this point, u1, and the other is the displacement of this point, which is u2, which means now this spring is extended by u1, so it's going to apply a force ku1 here. This spring is displaced by u2. This is going to apply a force ku2 here, and then to balance these two forces, you need a force ku1 plus ku2 at the support point in the other direction. So this is the reaction force. On top of that, this is a rotational spring. So if this undergoes angular displacement of alpha, then this rotational spring will be subjected to kr times alpha, which is a moment that's going to be applied at this joint. Now, under these action of these forces, it's going to be in equilibrium, but we will take the energy root, and what we are going to look at is um, what we are going to look at is the total potential energy, which is strain energy stored minus the potential of the loads. The potential of the loads is this point has moved by some distance. So let this distance be delta V, and the potential of the loads is simply P times delta V. We will try to calculate delta V. We'll consider these angles alpha and beta to be small. So again, let me clear this. Again, if this is u2, this distance is u2, then this distance is 2u2. This whole distance is u1. So alpha is equal to u1 minus 2u2 by L, whereas beta is equal to u2 by L, provided that alpha and beta are small angles. To calculate the vertical displacement of this point with respect to this, we consider the fact that this was the vertical position of this angle is beta, and it was of length L. Now this point was at height L. I am exaggerating it a little bit. This point was at height L, and now it is at this height, which is L cos alpha plus beta. So it has come down with respect to this point by L minus L cos alpha plus beta. Similarly, this point with respect to this point, this was at a height L again from this point here, and it is now at a height L cos beta, so it has come down by L minus L cos beta. So delta V, which is the vertical excursion of this, is a sum total of these two, and we will assume that these alphas and betas are small, so cos x can be written as 1 plus x square by 2, and so on. So alpha plus beta square by 2, 1 plus alpha plus beta square by 2, and then this is 1 plus beta square by 2. We will make these approximations and then use the approximations for alpha and beta to express the work done by the external force P times delta V in terms of U1 and U2. That's what we do in the next slide. So we have this delta V, which, as we just explained, is this. We make the approximation that alpha plus beta is small, then delta V comes out to be this quantity. And then alpha we have already found is this, beta is this, alpha plus beta is just the sum total of these two, and it is given by this. So the potential of the external loads is W delta V. On the other hand, the strain energy stored in the system is half k u1 square for this spring, half k u1 square for this, half k u2 square, and for this is half kr alpha square. So these three things would constitute the strain energy stored in the system. U minus W has to be a minimum. Now there are two generalized displacements, U1 and U2. So we will have to calculate del pi del U1 equal to 0, del pi del U2 equal to 0, and these would give me the equations of equilibrium. If these two equations have a solution, different from both U1 and U2 not equal to 0, both U1 and U2 equal to 0, in that case, this sideways tilted, perturbed situation is valid, is an equilibrium configuration. If only solution to this set of these two set of two equations is u1 equal to u2 equal to 0, then obviously this is the equilibrium equation. The vertical solution is the only solution. Okay, so um, so we are going to impose this. We are first going to calculate pi as u minus w, where u is this, w is here, delta v is this, with these approximations. And when we do that, this is what the pi we get, and we set del pi del u1, and we get a 2 cross 2 matrix now. And if you can do the maths, it's simple. You have to take derivative of pi with respect to u1 and then with respect to u2, write them as matrix equations. Please try them out yourself. And then this is the set of equations that you get in matrix form. Now, the difference with the previous solution is that now on the right hand side, you don't have a set of external forces, but you have a force that is dependent on the displacements themselves, the generalized displacements themselves. In other words, if we call this equal to k, if we call this a k, if we call this generalized w, and this is u again, and this is, we give it a name, let's call it b, then this is a problem of the form ku equal to lambda bu, where lambda and p are the same things. Lambda and p are the same things. And this is what is known as a generalized eigenvalue problem. This generalized eigenvalue problem obviously will be satisfied when u is equal to 0. That means both u1 and u2 are equal to 0. Then you have a 0 equal to 0 form. But for this to be satisfied for a non-zero value of p, you will need special sets of u's, special combinations of u1 and u2, for which, and special values of lambda, or the force that you are applying at the top. For special values, you will have solutions, you will have non-trivial solutions to this equation. And these non-trivial solutions will occur for values of p that are called eigenvalues of this. And then for each p, you will get a u1 and u2 combination that will give you the eigenvectors, or these will give you the buckling loads and the buckling modes for this system. Okay, so there will be two eigenvalues and two eigenvectors, which means there are two buckling modes of this system. So this is an example of a problem which, when cast in matrix form, gives rise to an eigenvalue problem, and solutions to the eigenvalue problem gives you the buckling modes of the system. This is another set of problems that we will look at carefully in the days to come. So we have seen a problem where we are solving the static equation of motion, and we end up with ku equal to f kind of a solution. So this is the equation of motion. We have seen a problem, another problem, where we looked at the stability of a structure under particular loading, and there we ended up with an eigenvalue problem of this form. So the solutions to the eigenvalue problem give you the modes and eigenmodes and eigenvalues of the system. So let us look at a different kind of problem, where the problem is described in terms of a set of differential equations and boundary conditions. A very simple problem of heat transfer, where we have a fin, rectangular fin, whose perimeter, cross-sectional perimeter is P, and the cross-sectional area here is equal to A. So you have steady state heat transfer through this, and there is convection taking place from all over the surface, and this the ambient is at a temperature T infinity, which we for simplicity take to be 0. Okay, so the heat transfer the conductivity of this material is equal to K. The convective heat transfer coefficient is equal to H, and we can easily see that the governing equation for this problem is given here. We can easily derive it very quickly from steady state heat transfer considerations. So here is a small element of the fin, which is dx. We assume that the heat transfer is the temperature distribution is one dimensional, so temperature is just a function of x. It does not vary with y or z. With that assumption, the heat entering through the left side of this small element is q dot, which in terms of heat flux can be written as q dot times a. Small q dot is the heat flux on the left side. On the right side, the heat flux is dq dot dx into dx q dot plus dq dot dx into dx times whole times a. So this is at q dot at x plus delta x, and this is q dot at x. So this is the heat entering through the left, this is the heat leaving through the right, and on top of that there is heat convecting away from the body. Because of convection, it generally depends on the difference in temperature between the wall and the atmosphere, but the atmosphere we have taken it to be at T infinity equal to 0, and it's one dimensional heat transfer. That means the whole of the cross section is at the same temperature Tx, so the wall temperature is also T, and therefore the heat escaping is H times T minus T infinity, where T infinity we have taken to be 0. This is the heat escaping per unit area, and then you have to multiply it by P in order to get the heat escaping through the whole perimeter, entire perimeter of the system. Now, heat balance is heat entering has to be heat lost by convection plus heat leaving. This is what you have. Then q dot a cancels on both sides. T infinity is taken to be 0. So you have q dot dq dot dx. Oh, sorry, this is there should be a dx here. This is p times dx is the area. P times dx is the area. So dq dot dx into a plus pht is equal to 0 is what you will get. Okay, now use Fourier's law. Fourier's law tells me that q dot is equal to minus k dt dx. That is the Fourier's law of heat transfer. So heat conduction. So I have minus ka d square t dx square plus pht equal to 0. Take the minus out. This becomes minus. So this is your governing equation, which we write as d square t dx square minus ph by ka t equal to 0. This quantity, we'll give it a separate name, we'll call it m square, just for the sake of convenience. So the governing equation is d square t dx dx square minus m square t equal to. Now as for the boundary conditions, here the temperature is same as the temperature of the wall, which is given to be 0. So T0 is equal to 0. On this phase, what you have is heat leaving is H times A times T at L, and that has to be equal to minus K dt dx into A. These two things have to be equal. This is the heat entering and this is the heat leaving. They both have to be the same, which means the A cancels out, and dt dx at x equal to L has to plus h by k at t equal to L has to be equal to 0. So this is the boundary condition at x equal to L, and the boundary condition at 0 is given to be t0 equal to 0. So this completes our definition of the problem. So the definition of the problem is these two boundary conditions combined with this differential equation governing the problem. Once we have this, we can now strategize how to solve this problem. One of the ways of solving this problem, problems defined by differential equations and boundary conditions, is by a method called finite difference. So what we can do is we can divide first the whole length of the fin. It's a one-dimensional problem. Whole length of the fin into a set of equal divisions. So the length from 0 to L we divide in small steps of delta x, and then we consider a generic division which we call I. The previous one is I minus 1 and the first one is I plus 1. We start with 0. Therefore delta x is simply L by n. Delta x is simply L by n. Now because we have divided them very closely, we have used a very fine mesh, so to say, we can assume that the variation in temperature, which is the primary variable for which you are going to solve and for which you have our differential equation available, that temperature T varies linearly over this, and we can use several difference formulas to convert the continuous derivatives at x equal to xi into discrete derivatives. These are called difference formulas, and here what we are using is typically called it's typically called the central difference formulas, but there are other difference formulas like forward and backward difference as well, and these are also correct to the order of delta x square. So as delta x goes small, then these derivatives, then this almost equal to sign tends to an equal to sign. So these two derivatives start coming closer to each other as delta x becomes small. Obviously it comes close to each other as delta x square. If you want it to come close to each other as delta x cube, for example, then you would have somewhat different formulas for the first derivative and the second derivative. So to calculate the first derivative, this is the formula that we use. These, by the way, follow from the Taylor series expansion of T about the point I, and these are pretty easy to derive. So Ti plus 1 minus Ti minus 1 by 2 delta x is the so Ti plus 1, T here minus T here divided by this whole length, which is 2 delta x, is your approximation for the first derivative, and the approximation for the second derivative actually can be derived from the approximation of the first derivative, and it turns out to be Ti minus 1 minus 2Ti plus Ti plus 1 by delta x square. I'm not going into the derivation of these difference formulas. You can find them in books. If you are interested, I can give you the derivation. These are pretty easy to get anyway. So once we have converted these derivatives into discrete expressions in terms of the temperatures at the nodes, we can now write down the governing equation, which is valid all over the fin. This is the governing equation. We can now write the governing equation down at a point I. At a point I, we can write the governing equation down in the discrete temperature form. For example, if I want to write it at the point I say that at x equal to xi del square t del square minus m square t at I is equal to 0. I want to write this. Then I will write Ti minus 1 minus 2 Ti, I think that's what it is, yeah. Ti minus 1 minus 2 Ti minus plus ti plus 1 by delta x square minus m square ti is equal to 0. This is the discrete form of this equation. Now, note what I am doing. I am not demanding that this equation has to be valid all over this domain, but I'm not demanding, I'm not enforcing the satisfaction of that equation at each and every point. I am enforcing the satisfaction of this equation at points I minus 1, wherever my divisions lie. So that's where I am enforcing the satisfaction of this governing differential equation, though in reality it should satisfy it at each and every point. So my hope is that if I satisfy them at a large number of discrete points, the points in between will take care of themselves. They will not be very far off from the true solution to this equation. So we are satisfying it at this is the equation that we write at t equal to I, and we can then write it for t equal to 0 to start with and all the way up to t equal to n. So if we do that, then this is how it is going to look. This is the equation that we have for t equal to I, which is nothing but just rearranged form of this equation that I have written. So I have taken ti minus 1, ti plus 1 and ti terms together, and when you do that, this is what you get. This is the equation for I. Now if I write it for t equal to 1, let's say, then this would be t0. Then this quantity, I give it a name because this is a constant for every I call it d. So this would be dt1 minus t2. Similarly, for 2, this would be dt2, this would be dt2, this would be minus t1, and this would be minus t3. It will go on for n minus 1, this would be tn, this would be tn minus 2, and this is the system of equations that I will have. Further, we have at x equal to L, we have dt dx plus h by kt equal to 0, and dt dx at the last point we can write in discrete form as tn minus 1 by delta x, and then this plus 8 this is equal to 0 is my discrete equation, difference equation for the boundary condition at x equal to L. This equation allows me to express tn minus 1 in terms of tn, which means from this last equation, I can eliminate tn minus 1 and write it in terms of tn. So last equation will have tn minus 2 and tn only. Thanks to this equation, the first equation will have t1 and t2 only, thanks to the fact that t0 is known for this problem from the boundary conditions. So once these boundary conditions are known, boundary conditions are implemented, I can write this complete set of simultaneous equations in the form of a matrix. So the first equation is, this is for t1, this is for t2, that's the first equation, this is for t1, this is for t2, dn minus 1, and then that is equal to t0, whatever t0 is given as. I think it's given as 0 in this problem. For the last equation, this is for tn minus 2, tn minus 1 does not have an entry, and then this is for tn. So once we have this is called a tridiagonal system of equations. This is the diagonal, and then if you look at this system of equations carefully, you have one the diagonal just above it and diagonal just below it populated. So it is a matrix with this kind of a form where you have a diagonal and then the diagonal above and the diagonal below are just populated, and these are called tridiagonal systems. And if you solve these tridiagonal systems, you can solve for t1 to tn at all the nodes in your one dimensional fin. So there are special techniques for solving tridiagonal systems which are very fast and very effective, and it makes a lot of sense to convert the problem into this form so that you can solve quickly on the computer. Now, that completes the three problems that I wanted to do. And now, having got a flavor of how we do this conversion of a physical problem into a matrix set of equations, and the three kinds of matrix equations you have seen, uh, you will be in a better position to appreciate the way we do it in finite elements, which is where we are going to start in the next class.